Hello, everyone. I'm Ida Momennejad. Welcome to Microsoft Research Summit 2021. Me and my colleague Raluca are excited to tell you a little bit about our work on evaluating human-like navigation in 3D video games. I'd first like to thank our team, our wonderful team at MSR Cambridge, as well as our colleagues Ali Shaw and Gavin Costello at Ninja Theory for collaborating with us on this project that has been presented at ICML 2021. About 3.1 billion humans worldwide play video games. What we asked in our research was, can we explain what makes navigation human-like using video games and reinforcement learning? You might think passing benchmarks might be enough for having human-like AI. However, many AIs that pass task benchmarks do not necessarily show human-like behavior nor human-like mechanisms. And some of the algorithms that behave like humans have bad generalization to new tasks or don't have neurally plausible mechanisms. And some AI that has human-like or neurally plausible mechanisms may not have neurally plausible behavior. For instance, CNN representations are brain-like, but they don't show human-like behavior on adversarial attacks. So why navigation? We chose navigation in 3D space because it is a fundamental skill of embodied intelligence, and it's well studied in both biological and artificial agents. And even in biological agents such as rodents and humans, it has been studied in virtual environments, making it very plausible to study navigation in a virtual setting like 3D video games. We will first tell you a little bit about the architectures of agents that we tested in our game settings and the human studies we conducted to judge whether the behavior of those agents is human-like, and finally, artificial judges that evaluate the human-likeness of navigation of those agents.
Hi, everyone. Thanks, Ida. I'm going to briefly talk to you about the agent architectures that we developed with reinforcement learning. To give you a brief introduction of the environment that we chose, this is Bleeding Edge, the latest release from our colleagues here in Cambridge at Ninja Theory. In a nutshell, it's a 4v4 multiplayer online game with a wide range of cyborg superheroes, 2 different game modes, 7 maps. And as a quick disclaimer, we just want to say that we use this purely as a research platform. None of the agents that we will show today are planned to actually end up in the game. I'll briefly introduce the navigation task that we chose. So we are in the single agent setup. In the screenshot, you can see the agent navigating to a cluster of seeds. That's the goal where it has to get to on the map. On each episode, it spawns on one of the aisles, so that's separate from the main map, and it has to learn to navigate onto the main map. And these cluster of seeds can actually spawn in 16 possible locations. The agent has access to a discrete action space. It can move forward, left, or right to different degrees. And in terms of rewards, it gets an incremental reward for getting closer to the goal, a negative one if it moves away from the goal, of course, a reward for reaching the goal, and a negative reward for actually dying, as it can jump off the map as well. We developed 2 artificial agents. The first one is the symbolic one. We call it symbolic because of the symbolic observation space that the network perceives. That's represented by 6 floating point numbers, the relative goal position, the angle and distance of the agent towards the goal, the visual frame average depth, 1 value, and the absolute position of the agent, XYZ coordinates. We pass that through a set of fully connected layers, and we get a next action prediction. The second agent is the hybrid one. So in addition to the symbolic values that I presented in the symbolic agent, we now add visual input. That's represented by the depth buffer. We center crop this image and we resize it and we pass it through some convolutional layers. That gets concatenated with the symbolic information. And that's how we get the prediction again. This is helping the agent to get a bit more understanding of its 3D environment and any obstacles and how close they are to the agent. In terms of performance, we can see here the time to goal. In orange, we can see the performance of the symbolic agent, and in blue, the performance of the hybrid agent. They both reach the goal in similar times, and what's important to note is that they also can be easily compared in terms of numbers to the time that a human takes to reach the goal. And in terms of episode reward, that's the main metric that we use to analyze the performance of the agents. We can also see that both agent architectures have similar performance. What's important now to ask ourselves is they do perform similarly in terms of numbers, but qualitatively, how can we assess if they are human-like?
Thank you, Raluca. As Raluca mentioned, one of the most important questions in our work is whether performing a task is sufficient for having human-like behavior. To that end, I'm just going to show you two videos on the left and on the right. Please take a look at the video on the left, and then I'll play the one on the right, and decide which one of these do you think is more likely to have been played by a human. Note that in virtual reality, humans are more likely to navigate in human-like ways. This is the second video on the right. We are not currently live, but I'd like you to enter in the chat which of the two do you think, left or right, which of the two do you think is more likely to have been played by a human? So now that you have your guesses, I'm going to reveal that the video on the left was played by a human and the video on the right was played by an agent. Here are two other videos. You're currently watching the video on the left. It reaches the goal. Now I'm going to play the video on the right. Again, please indicate in the chat which one you think is more likely to have been played by a human. And in this case, I'm going to reveal that these were both agents, and one of them that was the hybrid agent, and that was on the right. And in fact, a lot of people think that that one is the one that is played by a human. This is exactly the structure of the experiment that we conducted. So people watched two videos side by side, and then they indicated which one of them is more likely to be played by a human. And after that, they indicated why and how certain they were of this decision. In the first study, we directly compared human versus hybrid agent on 6 trials. And in 4 trials, we compared hybrid versus symbolic, unbeknownst to humans, subjects, that some of these trials were human versus an agent and some were two agents versus one another. Similar structure in study 2, similar number of participants. And in this case, the main sort of human comparisons were against the symbolic agent and on 6 trials and then 4 trials of the two agents. Here you can see the main results of agreement with ground truth. This would be the result of a Turing test. If an agent passes the Turing test, then it should be performance of all the human judges should be around 50%. As you can see, judges are around 80% or more in terms of performing, in terms of judging whether an agent, whether it's a human or an agent playing. This is only on trials where an agent was compared to a human. And as you can see, they are pretty much comparable in both study 1 and study 2. So people are very good at distinguishing human versus the agents. And they're somewhat more uncertain in study 2, but broadly similar. However, when you look at the comparison of the two agents, and here on the y-axis, you see number of times an agent was judged to be more human-like, in yellow for the symbolic and in blue for the hybrid agent for study 1. This shows that out of our 30 subjects, there was an overwhelming larger number of times that people thought the hybrid agent was more human-like. And the same pattern held for study 2, slightly better performance for the symbolic agent, but overall the same trend holds. People seem to find the hybrid agent more human-like compared to the symbolic agent, even though they are equally good at distinguishing them from human performers. So what do these evaluations mean? Can we make that automated? So we attempted to design artificial judges of the navigation Turing test in order to generalize human-like navigation. We had different judges designed who received either symbolic information about the agent's visual input, top-down trajectory of the movement or the policy that the agent took, or a barcode trajectory that averaged the movement of different images. The results that we observed was that some agents performed better than others. However, all agents were better at determining which one was the human agent, but when it came to hybrid versus symbolic, they were all at chance or worse. Therefore, what we observed as in summary was that human models have the highest accuracy on the test set. They all performed poorly when they were asked to differentiate between the two agents as opposed to the two models. Finally, symbolic and top-down models are most correlated with human judges' human likeness judgments. And this has opened up a number of different research for the future, because it would be wonderful if we have an agent in the future that can meta-learn how to behave in a human-like way by judging its own human likeness in a game. Conclusion, deep RL agents can learn efficient navigation in 3 environments, and humans can reliably tell the difference between human gameplay and agents. And high skill in passing a navigation benchmark is not enough to reproduce human-like behavior. And and artificial navigation Turing test, the one that had artificial judges, can learn to discriminate humans from agents, but it remains an open challenge to automatically rank agents in terms of their human likeness. And improving ANTT could help us understand how humans assess human-like behavior and improve adversarial imitation learning methods. Thank you so much.